So in class, we either have discussed or will discuss, depending on when you view this video, the idea that there are two typical types of problems that involve the normal distribution. In the first type, you're given a z-score or value, and the goal is to use the CDF function to compute an area or percent. So for example, given a value of z on the x-axis, how would you find this corresponding shaded gray area, the y-axis? But there's also the other problem, which we call inverse problems, which work in the reverse direction. We're given an area or percent, and we use the inverse CDF to find the z-score value. So in these problems, it's more typical to be given this area, and the goal is to figure out which value of z would give us the appropriate cutoff. This week in lab, we're going to explore how to use technology to answer both types of problems. So to begin, open up RStudio, and in today's lab, as I mentioned, we're going to learn how to use RStudio to answer problems involving the normal distribution. And along the way, we're going to learn about two new features of R, which are the ability to create script files, which are basically blank files in which you can store sequences of commands so you can execute them again in the future without retyping them into the window. And we're also going to learn about plotting in R. So to open up a script file, click on File, New File, Rscript, and you should see a blank file appear in the upper left corner of the window. And what we're going to do first of all, in a script file, if you put a # before a line, then that line will be considered a comment, so a note to yourself basically, and will not be a command that's actually executed by R. So what we're going to do first is we discussed in class the phi function for the CDF for the normal distribution. We're going to use R to compute phi of 1.6. Right. Basically in R, the CDF goes by the name of p-norm for probability normal. And it simply accepts a single argument of 1.6. So if we enter that and highlight it and click 1, we can see that R will compute the CDF of 1.6, and we get a value of almost 95%, which means about 95% of the time with a normal distribution, you'll get an observation that is 1.6 or smaller in terms of z-scores. Okay. So what we'd like to also do in this lab is create a plot which visualizes this probability. And in R, there are a couple methods of plotting. The one I'm going to use today is similar to MATLAB and also similar to what you did in high school when you drew the plots of a function, which was you create a vector of y values or a list of x values, and then you compute a function at those x values and then plot the points x comma y. So to create a sequence of x values, we use the seq command in R. We're going to start at -3.5 and go to 3.5. And we're going to create our sequence by skipping by increments of 1/100th. So if we highlight this and hit run, we can see over here a new value x appears in our environment here. And notice that the entries of x, it has length 701. The first entry is -3.5 and then increments up by 1/100th to -3.49 and so on. Okay. Now to create the vector of y values, we discussed in class the form of the normal distribution function as 1 over square root of 2 times pi times exp of -x squared over 2. And in R, if you simply type the function using sqrt for square root, pi is simply denoted by pi, and exp is the exponential function. Highlight and run. Now R has computed for us a vector of y values where each y is, well, we plugged in basically the value of x into this function to compute the corresponding value of y and did that for each number in our list. Now we just simply use plot x comma y, and we see that R will create this bell-shaped curve from -3.5 to 3.5. Now we could tweak this graph a little bit. You notice that right now it's using solid, actually open black circles, but it sort of looks thick. There's a number of ways to change this. The plot function in R has quite a few different options, and if you click Help Plot, you can see what some of those are. And you'll notice if you scroll down the page that one of these is type. The default for type is points, but we can change that to lines, which will draw a more solid line graph, which is kind of what we're more used to when we draw the graph of a function. So if we go back up here to our script and change type to L, and then re-execute the command, notice now I have a plot of the normal CDF with this nice smooth curve instead of what I had before. You can also change the values on the x-axis. For example, if you want the x label to be the z-score, we could do that. And on the y-axis, we probably want it to say something else as well instead of just y. This is actually the density, or sometimes you say the probability. So put density there as well. And now we have a nicer labeled plot. And of course, you can do other things like change the font types and change the labels on the axes, but I'll let you explore those options on your own. Now that we've plotted the normal density function, the next step is we're going to shade the region to the left of 1.6. And perhaps for the lab assignment, you may need to shade a different region, but we'll do the one that we computed earlier, just to demonstrate what this computation pnorm 1.6 is actually telling us. Now in R, the best way to shade a region is via the polygon function. And the first two arguments in polygon are the x and y coordinates of a polygonal region. And the third is a color with which to shade that polygonal region. Now I don't want to use x and y here because x and y were these, and those are the points on this curve. What I want to do is define a new x vector which starts at the left hand of my curve and ends at 1.6, because that's the boundary of the region I'd actually like shaded. So I'm going to create a new vector x1 in the same way as before, but instead of going all the way to 3.5, I'm going to end the sequence at 1.6, still incrementing by 100. Then I'm going to cut and paste my previous command where I defined y, redefine this as y1, and change x to x1 here. And now in my polygonal command, what we're going to do is do polygon x1, y1, color equals blue. Now this is not the right thing to do, but I'm going to show you just to kind of illustrate what happens here. Notice that what it did was it colored this polygonal region, but it didn't go all the way down to the axes. And that's because what we need to do is start off the polygon at this left-hand point and end it at the point 1.60. That's a pretty easy fix in R. We're going to use the concatenate function, which is just simply C, to concatenate on the endpoints of the interval to x. So this is going to add negative 3.5 at the beginning of x1 and 1.6 at the end. And we're also going to concatenate on the endpoints of the y interval to y. So that means we'll start on the x-axis and end at the x-axis. So now, if I recompute this, notice it does actually shade the region. However, it does leave this messed up region here. So what we really should do is rerun our plot function, create a new plot, and now run the correct one. And you see here, voila, that we end up getting the region shaded from 1.6 down to illustrate the area that was computed earlier using the CDF function. The final part of today's lab is solving inverse problems using RStudio. So for example, to illustrate this process, what we're going to do is we're going to solve the problem find z for which phi of z is equal to 0.97. So essentially we're trying to figure out which value of z, right, has an area to the left of 97, or which value of z represents the 97th percentile of the distribution. The function in R which computes inverse probabilities is called qnorm as opposed to pnorm. And to use qnorm, you simply enter the percent as a decimal that you'd like to find the corresponding z value for and run. And so in this case, 1.88 would be the 97th percentile, or the value which has 97% of its area to the left for the normal curve.